So today is, what's today?
18th.
2011, and we are just talking about limits and continuity.
So way more fun, awesome.
Exactly.
With limits
and continuity, electric boogaloo.
So are we going to go over the homework here?
Pardon?
Are we going to go over the homework, or do you?
We're going over the homework first, and I want Parker to be able to see that. So that's what we're doing. Okay, so starting with number 48, working backwards. Okay, what was number 48? And what page was it on?
It was
1060.
1060. And 48. Okay. F of x equals, big bracket, x squared minus 16 over x minus 4 if x is not equal to 4, and f of x equals 7 if x is equal to 4. Okay. The first thing you need to see, do you think this can be simplified?
Yes.
Okay, so let's start with that. X squared minus 16 over x minus 4 equals x plus 4 times x minus 4 over x minus 4. You see your a squared minus b squared factoring pattern. From there you can cross out the common factors top and bottom, and what you should hopefully take from this is that this rational expression is exactly the same as the line 1x plus 4, except for at one spot. And where is that spot?
At 4.
Like
4.
Yeah, 4.
4.
Yeah, that's your y.
So,
Intercept.
you know, as long as x does not equal 4, which is good. This rational expression takes this into account.
But then there's no b. Then the b is 5, not 4.
What are you talking about?
mx plus b?
Yeah. If the b, the begin at b is 4, but you can't be at 4, then it doesn't begin at 4.
Is b a y-intercept or an x-intercept? And this is an x value, and b is a y value. So they can do two different things on two different axes.
Wait.
You were so passionate about it that I hesitated to correct you.
At first I thought she was kidding. She was so like,
I know, I thought you were like in a... stay passionate, Janelle. Okay, so...
wait, do we have to whenever we have like x squared minus 16, because we don't know how to graph that, do we have to do that?
Well, actually, you would know how to graph this the way we did rational expressions a couple of tests ago. But in this case, but always try to simplify it first.
Yes, your test.
So this is a line with a hole. Yes, your test, yes. Now, okay, the questions are, what is the limit as x approaches 4 from the left?
4.
And so it looks like either you graph the line x plus 4. Well, let's see, if it behaves like this line, what happens when I plug 4 in for x?
8.
8. So this thing is really going to head close to 8 as we get close to 4. We can't actually reach it.
But what about the 7? We don't do anything with it?
No, it's not yet. Not yet.
It's just a point.
Yeah, what this is going to look
You're
like,
just a point.
if I may draw it quickly without putting in the axes, is this would be the point 4, 4, which doesn't exist, and up here above it would be the point 4, 7, just sitting there, just up there. I can't think of anything what it's doing up there. Just chilling. And now the next question is, what happens as you approach 4 from the right?
Wait, isn't it 4, 8? The y-intercept is 4 and it goes
Thank you, Ramsey. You know, I just made the same mistake I heard. Yes. Okay, so 4, 7, it's actually down here. Okay, and then it's what happens when we approach 4 from the right.
Why would it be 4, 8?
Because it behaves just like the line x plus 4. So as you get close, as x gets close to 4, x plus 4 gets close to 8. So as we approach 4 from the right, we're also going to get close to 8. And then the last question is, so what's the limit as we approach? 4 from both sides.
Mr. Belleville,
Yes.
why is finding the limit of a function so beneficial?
Tomorrow we're going to start talking about that in great detail. I'm going to give you a problem that sounds simple and that applies to things that happen every day, and show you how if you don't use limits, it's impossible to solve.
God, thank God I'm not here.
Alright.
I'd get pissed off.
Yeah. Okay, so this is how you answer the 3 questions on 48. You didn't necessarily have to graph it. I find this little illustration helpful. If you know you can simplify it, then you can get something simpler to work with. And I hope I didn't have to point out, because I didn't say at the beginning, that the problem was, as you get close to 4, if you just plug 4 in for x, you get 0 over 0, and it's expressed this way.
Wait, is the buttonhole at 4/8?
Yes, the buttonhole discontinuity is at 4/8.
Wait, it starts at 4, right? The line.
Yes, this line would
So
hit
it's a
4 on the
4.
y-axis.
And
go
then
through 4.
wouldn't you go 1 up, 1 over, 1 up, 1
Yep.
over? Oh, okay.
And then you hit 4/8. But
So it helps me to graph it.
this piecewise function says when you get to the buttonhole, drop 1 down to 7 instead.
Okay.
44. We do a couple more of these, I hope. 44, is that another? Yeah, it's another piecewise with 2 lines. Okay, I may have to graph this one. F of x equals.
Wait, we didn't do.
We didn't have to do 14.
We did 42. Thank you. Thank you very much. Oh, and 42 is the one I really wanted to get to.
Yeah.
Okay. That was to find the limit. There's a factoring pattern in this. Here. Give me 3 tries and I'll write it correctly. Alright, the limit as x approaches 1 of x squared minus 1 over x cubed minus 1. First thing, check. Is there a problem?
Yes.
Yes, you put in 1, you get 1 minus 1 over 1 minus 1. You cannot say it's equal to 0 over 0 because that says nothing. Well, it says anything actually, which is literally mathematically worse than nothing. But how can I factor the top?
X plus 1, x minus 1.
Okay, we did this briefly. I don't blame people for not remembering it, though it's worth looking up if you don't. We did look at this factoring pattern. A cubed minus b cubed. And it was a minus b times a squared plus ab plus 1, and this is never reducible any farther. That's a rule. If you break down, if you have a cubed minus b cubed, after you pull out a minus b, the quadratic that remains is a parabola with no x-intercepts. It never has any solutions.
I thought it was x minus 1, x minus 1, x minus 1.
Nope. No, 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 no.
What would that make?
Ah! Do you remember binomial expansion?
Yes.
Pascal's triangle?
Yes.
Remember making the 1, the 1, 1, the 1, 2, 1, the 1, 3, 3, 1? This is your Pascal's row of cubic coefficients. So x minus 1 cubed is 1x cubed, goes plus and minus 3x squared plus 3x minus 1. And if you don't believe me on this, you can double check me by going x minus 1, x minus 1, x minus 1.
I don't believe you.
I know this is kind of weird to mention now, but when it's a third, like the exponent is 3, it's 1 less terms.
This is a plus b to the 0, because anything to the 0 is 1. So the second row is a plus b to the first.
But then there's 1 term, no, well, 2 terms.
A plus b squared, that gets you 3
Yeah,
terms.
there's 3 terms.
Oh, the number of terms,
Yeah,
yes.
isn't that weird?
Yeah, cubic gets you 4 terms, quintic gets you 5 terms. Yeah,
No, quartic gets you 5 terms.
quartic gets you 5 terms. I had the right number, the wrong word. For the final exam in 2 weeks, binomial expansion. Nicely done, Janan. Okay, so but this was a factoring pattern we briefly talked about. So now I can cross out the x minus 1, and this x minus 1 factor turns out to be the one that was creating the 0 over 0. That's where the 1 minus 1 came from. This is where in the numerator. Here's where the 1 minus 1 came from in the denominator. So now, if I let the dog off the leash with my remaining factors and plug in 1, what do I get?
1/3.
1/3. 2/3.
2/3.
Yeah.
It's not 0 this time. So that's 2
Bad,
over
Nikki.
3. So it approaches 2/3. It is another buttonhole or removable discontinuity. If you were to graph it, it would look like this function with a buttonhole there. This would be a pain to graph because there's no zeros on the bottom. Without a calculator, it'd be annoying. But the limit is 2/3. Any questions on that one?
So anytime I asymptote, is that 2/3?
No, horizontal asymptote.
I don't understand the
No, because I'm sorry, guys, you stumped me for a minute there. The horizontal asymptote is actually the limit as x approaches infinity. And this is only as x approaches 1. This is just a graph that would normally go to 2/3, but instead there's a buttonhole there because of the x minus 1 factors. But the horizontal asymptote would be 0, as you remember, because there's a lower degree on the top than on the bottom. Remember that rule? Okay. Any questions on 42? It really came down to, did you remember this factoring pattern or not?
Nope.
Are we even doing that for the exam?
I mean, I think
Could come up. Anything's fair game.
It's the same thing as taking out x, like one of them, and making it x squared minus 1 times x minus 1.
No, this is not x.
No.
No, this is not x plus 1 squared. There would be a 2 there,
Yeah.
and this would be this would have zeros.
Crap, I
And
don't.
it would be awesome.
There's not really a great mnemonic for it. There really isn't. It's just an annoying factoring pattern. I think I can do one more before I should get to, and then that one more would be number 34.
Yes, please.
Okay.
No, wait, no,
We didn't
36,
do that.
36.
36. Thank you. I'm not doing a terrible job of subtracting by 3. By 6. No wonder I'm doing a terrible job. Okay. They're all multiples of 6. It's all after now. Okay, so 36.
It's the limit. You want me to read it?
Thank you. Yes.
The limit as x approaches 3. Okay, there's a
Complex fraction.
1 over x
Uh-huh.
minus 1/3
Okay.
This one's fun.
over x minus 3.
Right. First thing, always check first, is there a problem? Great trick question. And make it the limit as x approaches 1, and there's no problem. It would just be, you plug in 1, you get a number. But it is 3, which gives me 1/3 minus 1/3.
0.
0.
0 over 0.
Yep.
Yeah.
Yes, it does.
So, the strategy I recommended for this was,
Get rid of the.
X in the
Yeah.
denominator of the complex fraction.
yeah, and I think I started by making a common denominator, right?
Yeah, you did.
Okay, so that's 3 over 3x
I got
minus
1 over x over
x
3.
over 3x, still over x minus 3. So that's 3, here we go. I'm gonna,
3 minus x over 3x.
yeah, I'm gonna do another step in here as well, if that's okay. May I take this denominator and change it into multiplying by 1 over x minus 3?
Sure.
Okay, good, because that just helps my brain see it better. And then this becomes 3 minus x over 3x. Okay, did anybody get stuck here or thereabouts? Okay, good. Here is
Wait.
the annoying...
If you're multiplying and you have the same thing on the denominator and numerator,
You
can
can
close
cancel them out. But
Yeah.
are these the same thing?
Oh no.
Not quite, but they're close. Okay, here's where people got stuck. Here's the trick. All right.
Would it just be -1 on top?
Nick's got it. Nick saw it first. 1 over x minus 3. Okay, on the top of the second fraction, I'm going to make it -1 times x minus 3.
There.
Do you guys see how x minus 3 is the negative of 3 minus x?
Yeah.
Yeah.
Okay, so you did have the same thing top and bottom. Actually, you had the exact opposite top and bottom. So what you have is -1 times x minus 3 here. Now you can cross out these factors.
No way.
And now you have,
-1/9.
yes, the limit as x approaches 3 of -1
Because
over
you let
3x.
the dog.
We did not do that strategy. That did not come up.
Oh, we did something like that.
Gross, and then you.
Yes,
Oh,
guys, stop. Okay. There is, we did one yesterday that was, the problem worked out very similarly, but it didn't have a -1 on top. Yeah, I did the example next to it.
And then you let the dog off the leash.
Yes, now as Alva said, you let the dog off the leash, and you let x equal 3, and you have negative 1/9.
I actually got it
Excellent.
last night. So give me a high five.
All right.
Seriously.
Sorry.
High five. Or as Megan put it earlier today, helping out someone else, I like what she said. Keep simplifying, keep simplifying, keep simplifying, and when you can't simplify anymore, if you've done it right, you'll be able to plug in the value and get something that works. Okay? But to do that, you've got to know every single trick for simplifying, including that x minus 3 is the negative of 3 minus x. Yes, sir?
For the top part of it, if you decided to let the dog off the leash there, you would have gotten undefined instead of 0.
No, because of this. What I would have gotten is
That's a bad
one
one.
over 0 times 0 over 9. Yeah. And so I still would have had a 0 on top and bottom. I still would have had a 0 over a 0. So I still can't go there. Otherwise, the limit, if that were true, the limit would be undefined. It cannot be both undefined and negative 1/9. So
Can
there
you-
can't be any other.
Wait, can't you cross them out, though?
Yes.
Can you cross them out though? The
The
zeros?
zeros? No, you can't. They don't work that way. They're not numbers.
If it's
Isn't that
undefined
crazy?
at the top,
Yeah.
Wait, no,
would it still
zero's
be
not a number?
undefined?
If it's 0 on top, it's just 0.
No, if it's undefined from the very
Mine
beginning
is
of the
just
equation.
Oh yeah, if it's undefined from the top of the equation, yes, I understand. If it's undefined in the first step, it is undefined, and you may want to do some checking on whether it's positive or negative in infinity. If you get undefined in the first step, then you've got a vertical asymptote, which means your function is either heading up towards infinity or down towards
How do you know where
negative
your
infinity.
vertical asymptote is? That?
That would just be zeros in the denominator.
Huh.
That's something else. This doesn't necessarily behave that way. You talked about this more in calculus. I wasn't actually going to get into this, but there's some controversy about vertical asymptotes and limits and how they're taught. So we're not going to combine the two. For now, just get to the number. We will talk, well, I don't think we'll have time to talk about that
Well, I'm not
this
supposed
year.
to put the limit.
Can be. A horizontal one always is. Vertical one, it's a little tricky.
I have a conceptual question.
Okay?
How does something that first equals 0 over 0 equal negative 1/9? Like, how is that possible?
Well, in all of these cases, you have some sort of removable discontinuity.
So you're just taking it out.
Wait, that's
Yeah.
a
It's
physics
just
word.
weird.
Well, it's you have some sort of buttonhole in basically all of these examples where you can do it. And if you can't do it, you don't have a buttonhole, you have a different type of problem.
So would you ever give us one where it would be like 1x or something?
No, I'm not going to give you one where there's not a way to remove the discontinuity this year. Next year in calculus, you start learning a couple of other strategies, the easiest one being what's called L'Hopital's rule. And that is a way to take anything like this and find out if it has a limit, if you can't factor out the discontinuity.
He was a G.
He didn't come up with it. There was no such thing as copyright laws. You got stuff named after you if you were the first one to put it in a popular textbook.
He was a G.
Yeah.
He
Okay,
must have been
so
smart enough
I was
to
circling
understand.
the
yes, and in that period that was impressive. Okay, I'm going to stop here and go on to the first use of limits, the first abstract use of limits. Tomorrow we'll do the first
Punchlines.
practical use of limits. Pardon?
Punch.
Punchlines.
Punchlines. There you go.
Movie quotes.
Yes. That's
I
right.
can't believe you don't remember Glen Coco. 4 for you, Glen Coco. You go.
Okay,
Mean
now,
Girls.
guys. Okay, when you get to calculus and beyond, it is hugely important that you know whether the function you're looking at is continuous. Continuous. The informal definition. Well, first off, it's a continuous function. That's important because lots of things are continuous without being functions. Informal definition is if you can draw it without lifting your pencil. It is continuous. You can draw it without lifting your pencil. It is continuous.
So like a line.
A line, every line. Good. Hang on. Let's.
I remember that pumpkin contest that we had to draw without lifting our pencils.
And if you could do it, then it was continuous. a lot of the math on the screen in Goodwill Hunting at various times was a different type of continuity that involves combinatorics. There's a famous problem named after a German city with 7 bridges over canals. And there was a question, could you walk in a circle across all 7 bridges without crossing one bridge twice? And it's considered, it's a really hard math problem. It's called combinatorics.
Why don't you try doing it?
Yeah, why don't you just go for a walk?
It's a little more complicated than that. At any rate, that's another form of continuity. That pumpkin drawing one is more like that type of continuity. It's not a function continuity, but that's a whole other realm of math. And some of it was on the blackboards in the background in Goodwill Hunting.
Did you pause it and figure it out?
No, combinatorics that's really never interested me much, actually.
I did it. I figured
okay.
out you can.
Woohoo!
I think.
All right,
Wait,
now,
there's
here's some
something-
examples of some continuous functions, okay? Lines, mx plus b, y equals 5, they're continuous. All polynomials are continuous, all through their domain, okay? Square root functions are continuous all through their domain, even though they don't exist everywhere. Cube root functions are continuous and exist anywhere. A sine wave is continuous, and there's no holes, there's no buttonhole discontinuities, there's no vertical asymptotes.
What about polar? No, nothing polar is.
We're sticking with Cartesian here. This is just rectangular continuity. Not going to do any polar or parametric
Are there
continuity.
limits for polar?
Yeah. We offer at this school AP Calculus AB. There is a harder version of AP Calculus called AP Calculus BC, in which you rush the first part of calculus, and the last part you do the calculus of polar coordinates, parametric equations, and sequences and series.
At least it's a little more interesting.
Yeah.
Would Johnny take that next year?
I don't know. No, probably not.
Then what would he take?
Well, I'll probably discuss it when I'm not taping it for the world.
Oh, okay.
Don't you mean Johnny Punjab?
Yes, and possibly maybe even discuss it with him first. Okay.
Possibly.
Yeah. Examples of discontinuous functions.
He's kind of.
Discontinuous functions. Things you should not be able to draw without. It's things you should have to lift your pencil to draw.
Ooh.
Yes.
Hyperbola.
Well, that's usually not a function, but the rotated one? Yeah, that's one. That's a good one. I was just first say removable discontinuities.
Piecewise function?
Depends. That's a good one. Removable discontinuity. 1 over x. This is actually in a category though, Janan. This is any rational expression with a vertical asymptote. Any rational expression with a vertical asymptote. Also, tangent x, cotangent x, secant x, very good, and cosecant x. Yep, those all have vertical asymptotes. They are discontinuous. You cannot run your pencil all the way up to positive infinity and then bring it down to negative infinity without lifting it.
But I thought tangent was just ballerina.
Tangent is a ballerina here in between negative pi over 2 and pi over 2, and then it repeats.
Oh.
And I'd have to lift my pencil to keep drawing it over and over again.
So can you just like the curvature, is that very different than cube root? I mean x cubed?
In College Calculus 2 or at the end of AP Calculus BC, there is a way to approximate certain other functions with polynomials. In other words, there's a way to get a cube root function very close to a tangent. But it's a never-ending polynomial, so that's why it's covered under sequences and series of calculus. That's actually a whole fascinating study, and believe it or not, that's the basis of the e to the I pi minus plus 1 equals 0 equation.
Which I just derived myself.
You have to approximate other things as polynomials to be able to find that. It's crazy stuff. I love that stuff, actually. Okay, so these are things with discontinuities. What else? Kath, you mentioned piecewise functions. piecewise functions sometimes. Do you remember how, it's got to be sometimes, you can't remember this always.
Yeah.
Remember how yesterday we did one on the board where it lined up. The two dogs met at the same point in the fence.
But you still picked up your big boy.
Well, I was drawing it, but I could have, but once I knew what it looked like, remember the first one we did, the parabola that went into a line? If I wanted to, I could have drawn it parabola, 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 line, and not picked up my pencil. So this one would be continuous. This would be a continuous piecewise function. But if I'd set up the function differently and made it so I had to go parabola, 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 stop, go up here somewhere and start the line, this would be a discontinuous piecewise function. So they can be either. They can really be either. And in fact, there will be some questions like that about what do I do to make it continuous. This is all informal. Now I'm going to give you the formal. Okay? Follow me back over here to board 1. And there's no new math in this. It's just an application of what we've been doing. Okay. Difference between a mathematician and an engineer.
Wow.
Which one's the better one to be?
Engineers make more money.
Yeah, there's a lot more
Okay,
job
not for the money,
opportunities for
for
it.
like the knowledge.
Mathematicians, everything's very formal. It's got to be proven. Nothing is true until you absolutely know about it. An engineer is allowed to approximate, estimate very carefully. Can't just take a wild guess. But in math, nothing is true until you've absolutely proven it's true for all infinite possible cases. And in engineering, nothing works until you've done it 10 times and it hasn't blown up in your face. So, depends on your personality, which one you have you'd rather do. Formal definition of continuity. I want to make sure I say it the way the book does. Okay, first off, for continuity, and I've been kind of glossing over this, is defined at a specific point x equals c. The examples I've given so far were only discontinuous at certain points. They were continuous at other points. A rational expression is only discontinuous at its vertical asymptote. It has continuity everywhere else, where it doesn't have a vertical asymptote in between them. So those functions have discontinuities, but it's defined at a specific point. And here is the 3 conditions. 1, C is in the domain of f of x. So for a function to be continuous at C, C has to be on that function. For example, what function does that look like? Who remembers?
Square root.
Root x, right, this is the root x function. Is this function continuous at x equals -2? No, it doesn't even exist at x equals -2. It's got to exist to be continuous. So this function is only continuous from 0 over in the positive direction. So that's the first one. That's fairly obvious, but it's so obvious people forget to think of it. 2, the limit as x approaches c of f of x must exist. If the limit does not exist, then there is a discontinuity.
Everyone's
I know,
sweating.
everyone's like, oh, Lindsay, she's done so much for my job. I read about her in the tabloids and I can never hate her because of that moment. So the limit has to exist. And the main way we've talked about limits that don't exist so far is if the limit doesn't exist from the right, if the limit is not the same from the right as it is from the left. But then doesn't that make sense that that would be a discontinuity? So if the function goes here and then jumps to here, I can't draw that without lifting my pencil. So that makes sense. If the limit doesn't exist, there is a discontinuity there. If it does exist, maybe it's continuous. But there's one other thing that has to be true.
Limits are so demanding.
They are. They're so limiting. The third thing is the limit as x approaches c of the function must be the same as f of c, as what you get when you plug it into the function.
No.
So for these piecewise functions, we've done where you have a hole and then maybe the function jumps up to here, like the example we just did at the beginning of class. This fails the third condition of continuity. The limit exists, so it passes the second. The x is obviously in the domain. It's a place where the function exists, so it passes the first. It fails the third, because the limit is down here, is this y value, but f of c is this y value up here. So this would fail the third test of discontinuity. To have continuity at a point, I would have to give you a point, and you would have to tell me, for me to believe the function is continuous there, that that point is in the domain, that the limit as x approaches that point exists, and not only does the limit exist, but when you get there, the function also exists there.
Wait, so to prove that the limit exists, do we have to do the, as like, it approaches
You have
from
to
the
do
left
everything you
and
did.
right?
You have to do everything you did last night, yeah. It's all the stuff you've been doing for the last few days. If you can actually find a limit, find a number, you don't get 0 over 0, or you get 0 over 0 and you get rid of it, and that number is the same from the left as it is from the right, and not only are you headed that way, but you actually get there. You have continuity at that point. This is usually, obviously this is not used to go through all the infinite points in a function and check them all. What you do is you find a point where you think there's a discontinuity, and you try to prove it fails one of these three conditions. So mostly you'll be trying to prove whether or not there's a discontinuity in a point. But these are the three conditions. Is the point in the domain, is the, does the limit exist, and is the limit the same as what you get when you plug into the function? And that's your definition of continuity. In AP Calculus, this is always in the background, but it only bites you in the butt about half a dozen times. It's really kind of annoying, actually, but it's always there in the background, because what will happen is, everything you learn in AP Calculus, they'll say like, for a continuous function, this is true. Or where a function is continuous, this is true. And you'll just brush off that part of it. And then like half a dozen times you'll be like, oh crap, it's discontinuous there, so this wasn't true. So it's something that's sort of like you'll forget about because you won't have to deal with this for a month at a time. And then all of a sudden on one problem it'll be like, oh, there was a discontinuity there. Everything I thought I knew was wrong. So that's how this shows up in calculus usually.
Can you graph a dotted line?
As data. Or are you asking me if I'm physically capable of drawing dots on a board?
No, can you graph it as y equals? Take that away.
If there's like many restrictions, you can.
Sure, you know the simplest but most annoying way is what Janae was just saying, make a piecewise function with like tons and tons of things. There is something called the greatest integer function, which I skipped this year. I think I might have mentioned existed. It's like y equals weird bracket with 2 lines x, and when you graph it, x only exists on the integer values and doesn't exist in between. So this is
nice.
This is a very discontinuous function, and it's kind of a dotted line, but they're all horizontal.
With like steps.
Yes, it's also called a step function.
Yeah, we did that with Mr. Singer.
This is a common form of piecewise
I
function
love
also.
that.
Yeah, we didn't do that exact thing though.
You probably didn't see this notation.
No, but we did the graph.
Okay.
We did?
Yeah, this is the you know, I'm honestly not sure if I'm filling in the right side of this, to be honest. I forget. I'd have to double check. Yeah, it just goes up like steps. It is a function. Guys, is this a continuous function?
No.
No. The discontinuities are right on when you switch to integers. Is it continuous in between the integers?
Yeah.
Yeah, those little chunks are continuous. Pass all 3 of these tests. Here they fail, and the one that, the condition that these fail is number 2. The limit from the right does not equal the limit from the left, so the limit does not exist at any of the integers. Here's sort of almost your ultimate discontinuous function. It's discontinuous for every whole number you can imagine. On the homework tonight, what you're going to be asked to do is, let me double check the numbers, is to prove or disprove continuity. And
Do you want me to stop it?
1067, 2 through 32 even. Not yet, let me check that I... It's 2 through 22, what was it, 2 through 32 even, okay.
What page?
1067.
2 through.
A year after the Battle of Hastings.
That's exactly what I was thinking.
I know.
Shut up.
I once created a problem where the answer was 1066 and gave extra credit to any kid who knew the significance of the year.
Obviously, you don't remember freshman history, Alba?
Wasn't it the Crusades or something?
It was the
Battle
England.
of Hastings.
No, it was the Battle of Hastings when William the Conqueror
He was the last
beat the
person
Saxons.
to conquer
England.
England and
The last outsider to conquer England. They had some civil wars after that.
The English Civil War in the 18th century.
Okay,
the Glorious Revolution.
guys. Okay, shh.
William of Orange
Stop.
and Mary.
For 2 through 18, you are given a point at which you need to test for continuity, and for 22 to 32, you've got to find any discontinuities. And some of them are piecewise, some of them are polynomials, some of them are rational expressions. There's no there is some trig. There's one with a little bit of trig in it. Questions, comments, concerns, compliments? Oh my God! Stop. All right.
I hope that thing's off.
Yes.